adapt this response method introduced in this paper here to calculate this correlation function. I have it up here in case you've forgotten it. So the idea is we take a Hamiltonian H0, perturb it with an amount proportional to B with a perturbing function eta, which has some frequency components in it. And what we do after that is we time evolve under this Hamiltonian. Now, if you want to solve the differential equation, you have to go through the song and dance of a time-dependent Hamiltonian with a time-ordered exponential, but we hope the quantum computer will do this for us. And we measure the expectation value of A as a function of time after evolving under this Hamiltonian. Once we have this as a function of time, we do a Fourier transform to frequency domain to A of omega, and then we estimate chi of omega, the star of today's show, by just doing a simple division, assuming the system responds linearly to the perturbation. And this is our estimate of the function chi of omega in the linear response regime in the limit that the perturbation goes to 0. Great. Now let me take a step back and say why we are thinking of analog quantum systems. In particular, when we think of circuit model quantum computation, a primary interest is doing time evolution. And oftentimes we have to take the time evolution operator, e to the I80t, decompose it into a bunch of Trotter steps, and each Trotter step is a complicated circuit like this. And there are wonderful tools to do compiling and different algorithms to do this, but in an analog system, we get this directly, assuming H0 is a system Hamiltonian. So for the purpose of this talk, I will focus on the analog mode. Of course, there are trade-offs, there is noise and other things which make the future of this interesting. Great. So the other ingredient of my title was neutral atoms. Neutral atoms are a scalable platform for quantum computing. We have seen multiple talks showing us how each atom carries a qubit. They can be rearranged into arbitrary geometries, something like this to do two-qubit gate, something like this, like a square lattice for quantum simulation, or even a triangular lattice like that. And these things have been done for circuit model quantum computing. We heard Jonathan yesterday tell us about the progress with Ytterbium 171 and atom computing, where they have zone-based architectures to implement different circuits and have very, very good gate fidelities, as seen by this randomized benchmarking plot over here. Earlier this morning, Milan told us about this work at Harvard and Quera, where you could actually run one of these computers for hours and actually do quantum computation with them. So neutral atoms are great. However, remember we were talking about analog. So when we think of neutral atoms with Rydberg excitation, we get an Ising-like model. So the Hamiltonian for a square lattice kind of reads like this, where we have each atom has a ground state and a Rydberg state with a Rabi frequency omega 0 and a detuning delta 0 for the ground Rydberg excitation. We have these terms, a transverse field proportional to the Rabi frequency, a longitudinal field proportional to detuning, and these van der Waals interactions between atoms when they're excited to the Rydberg state. This particular thing, as I said, has a rich phase diagram. So this paper here found the phase diagram of this particular thing on a square lattice, and there were very interesting phases from a disordered phase to checkerboard phase, striated phase, star phase, etc. And these phase transitions are very interesting study, and we will take a look at some of these from our experimental results. But first, I want to pay homage to the fact that this particular analog mode has been used to study antiferromagnetic order in great detail. In fact, many of these phase diagrams were experimentally studied, for example, by this paper from Harvard, and around the same time, in this paper from the Institut de Optique, both with rubidium atoms. Fortunately for us, NERSC and Quera provide us access to these analog quantum computing devices with rubidium arrays. So I'm going to get a little bit of atomic physics in here. So here is a subset of the energy levels of rubidium-87. Now these two levels give us the hyperfine qubit, which is what one uses for these circuit-based quantum computing. These two levels give us the Rydberg qubit, which is what we use for analog mode. And if in order to do one of these things, one has to go this very complicated cycle of loading a magneto-optic trap, loading the tweezers, imaging, rearranging, etc. However, thanks to our friends, we can just focus on this small part here and write an analog program and do the science that we want. Therefore, our quantum computer is just a black box. And our friends at NERSC give us access to that. Okay, so with that in mind, let's talk about what we are actually going to do. So remember our analog mode Hamiltonian for the neutral atom array with Rydberg excitation. So we will focus on this on a square lattice, and we will fix the nearest neighbor interaction to be 3 times the Rabi frequency and a Rabi frequency of 2 megahertz, if you're an experimentalist. If not, just think of it as a number. And remember, you may have forgotten, our correlation function is really this chi of t, where A is the time evolved operator and B is the initial operator. Right, and for the purpose of what I'm going to talk about today, our operators will be these global operators, where A is a global Z, B is a global X, and an initial state will be the ground state of the system, or really an approximate one. And the reason we chose these is because they map really well to the system that we have in mind, which is the Queyras-Aquila system. So the A can be, we can measure A by doing a Z measurement, which is really imaging the atoms at the end, whether it's the ground state or the Rydberg state. And B can actually be implemented by using a global X perturbation through this laser here. And here is an example of one of these analog programs where these are the waveforms I plug into the system, and then hopefully I should get the answer that I want. Let me talk you through what these things actually mean. So the first stage of our program is a quasi-adiabatic state preparation. That's to get an approximate version of the ground state of the system. So we sweep omega and delta, so to a value omega 0 and delta 0, so that we implement this Hamiltonian and have hopefully prepared the ground state of the system to a reasonable amount of fidelity. But that's where the fun begins. Then we apply a frequency selective perturbation. As you can see here, this seems like a Gaussian sinusoid. It is. And we poke the system, and while we're poking it, we actually measure. So once we are measuring, we should actually get A of t, which is what will give us the answer that we're looking for. And what we found that doing this particular thing actually works really well, both in our simulations, and as I will show you in a minute, it works really well in the experiment as well. So with that setup, here is some experimental data. So what I'll do is, on the top row, I'm showing eta, which is my perturbing function in the time domain. It's a Gaussian sinusoid. And at the bottom, I have A of t. Now, there's a lot going on, so let me talk you through this. So, of course, the first part is the adiabatic state prep. So, eta is 0. I'm not really poking the system in the state prep stage. But you see the A of t actually changes. That's sort of a signature of the fact that we're adiabatically preparing the state. Then, once we are applying the perturbation, that's when this eta of t becomes larger. We are actually measuring while we do that. And over here, what I will show you is that here, the solid line, the bottom line plot is the state vector simulation. The green squares are the ideal short-phase simulation, assuming my experiment is perfect. They match. Obviously, they should, because it's an ideal simulation. But what I want to emphasize is are these orange circles, which is the experimental data. This is the experimental data measuring the response to this perturbed frequency. And a few things about the experiment. So we actually measured 64 times over a period of 2.54 microseconds. The time between these two measurements is 38 nanoseconds. This is pushing what our friends at Queyras suggested we could do. So, your machine is better than you think that is. And we've actually overclocked the quantum computer, and it works. I don't know if you've got classical computers. Can you overclock Pearl matter? Great. So this works. And the thing that I want to emphasize is that the oscillations that we expect in our theory are also seen in the hardware, even though they are damped, but we see that. And we can be quantitative about this by just looking at the Fourier transform. So here I have the same thing, just now Fourier transform. So here the dotted line is eta, the perturbing function in the frequency domain. I have a large Gaussian here. And these, the blue line, the solid line with the diamond is the state vector simulation, which shows me that I expect a peak somewhere. The ideal simulation also matches that, which is great. But in the experiment, we see a similar spectrum, although the peak is diminished, which is showing that my oscillations are reduced. So the key part is that we do get a similar spectrum from the hardware, which is why we believe that this is working really well. So this was one particular example of this. So let's actually go back to our original idea. But before that, I want to say that using this method, we're actually probing some of the energy differences from the ground state for a 3x3 lattice. That's what these lines are. And we are able to find this particular resonance with our experiment. Okay, so let's actually do more than just one particular eta. So here I have an example where we take different etas. So these orange Gaussians are basically the eta and frequency domain. So we park it around here, and then move it around. And then we measure the response, which are these curves here with the experimental error bars, by the way. This is experimental data, no theory here. And what we see is when we are below a resonance, we don't see any response. As we start to hit a resonance, we start to see some response developing, and then the response stays there. And as we sweep across the resonance, the response goes away. So this is A. But what we really care about is chi. So if I do the song and dance of linear response and divide and do all of that, and feel free to ask me more about this later, this is what we get. So this, my friends, is an example of chi of omega computed using an analog quantum computer. And as expected, we do see a resonance around 6 megahertz. And if you remember, if you don't like megahertz, this is about 3 times omega 0. So we do see a resonance as expected, and the probe around 3 is where the resonance is the most pronounced. Okay, so now we're able to map out chi. Let's actually study some physics with this. So here is an example where we try to probe a phase transition. Remember, this model has a very rich phase diagram. And in particular, if I just plot A of omega for simplicity for this system as a function of delta over omega, on the left, we have a disordered phase. That's here. On the right, I have a checkerboard phase. That's over here. And if we try to figure out what the peak of that resonance is, we see that it decreases in both directions. So as we get closer to the critical point, we see the peak frequency decreases on this side, and the same thing happens on the other side. This is suggestive of the fact that these two lines, which are just the line fits, would cross somewhere in the middle, suggestive of a critical point and a gap closing at a phase transition. So we are actually able to do this to study some physics and actually detect some signatures of a phase transition. Okay, so that's all I had to say. I just want to say that we used an analog system with an algorithm to measure the dynamical correlation function directly in the frequency domain. We saw some signatures of gap closing near a phase transition, and we could, as I showed you earlier, sweep the probe frequency to estimate correlation directly in the frequency domain. Now, I didn't say anything about noise. That's because everything I showed you had no error mitigation, nothing. It's just raw experimental data. The only thing we did was Fourier transforms. So we want to look at how noise affects our simulation, see if we need to mitigate errors. Finally, I showed you everything for a 3x3. So I had the training wheels. The question that we have now is, does this work with large systems, or does noise destroy everything? Does it work for longer times? Those are open questions, and we are trying to work on those. So that's all I have. I want to acknowledge the wonderful people I worked with, Effican, Katie, and Bert at LBL, Heba and Lex at NCSU, and Milan here at Quera. And also I'm grateful to NERSC for the Quantum Computing Access at NERSC program, in particular the award, and also for using Perlmutter, because there's a lot of classical simulation that goes into running one quantum program. That's all I have. Thank you. Feel free to reach out if you have more questions.
Plenty of time for questions. How do you expect the signal to change as you increase system size?
That's a really good question. We do expect that there'll be more degradation because atom loss increases a lot more, and the probability of each atom, even if you don't lose the atom, the probability of each atom not being where it is increases. So we expect it to degrade. But we have some preliminary data which is showing that this could work, but I'm going to wait for the data to tell the story.
Did you try making the detuning the time-dependent one instead of the Rabi?
Great question. So this goes back to what I was talking about earlier. We did consider that, but what we found in our theory simulations was that the response is not as strong if we do that. And we just picked the operators that gave us the strongest response, so we don't have to worry about, we can still see the signal in presence of the noise.
Is there a physical reason for that? The signal?
There are two physical reasons, one of which I can say, which is that the Z correlator, which is what we measure, is actually just smaller, and it's really, really small I have the picture here, in the checkerboard phase. It's not very small, but it's still measurable on the left side. But the other problem is there also seems to be more noise in that. And that maybe our friends can explain why. I don't know. It's a black box for me, remember?
Yeah. So as far as I understand, like this, the linear response kind of is picking up the ground state, like some kind of energy differences from the ground state to other levels, right?
Yes.
So do you think that the main problem for scaling to higher qubits will be that you won't be able to prepare the ground state because the band gap decreases exponentially with system size?
That is a problem, yes. However, what might be a mitigating factor is that we don't really need the full ground state for this particular correlation function. And in general, how well you need to prepare the ground state really depend on what operators A and B you're working with. So that's an interesting question to be explored.
So you showed also simulation on classical hardware. Did you need to do that?
Did I need to what?
Did you need to do the classical simulations?
Well, quantum computing is a limited resource. So we kind of want to know what we're doing before we run it on a quantum computer. So yes. And in some sense, the choice of the observables, the choice of how we design our pulses was informed by classical simulation. So we do need that. But in some sense, the whole point of what quantum computing is about is we use classical simulation as training wheels to optimize our algorithms and run it in quantum hardware. And what I'm showing you right now is where we still have the training wheels on. And that's why we need the classical hardware. The other thing I would say is the classical simulation is actually faster than the quantum simulator for these system sizes, even on a laptop.
Yes, what I'm asking is now that you've had time on the training wheels, can you predict for future runs, how much of this do you still need the classical simulations, or can the training wheels come off entirely?
That is the question, right? I don't have a good answer for you right now. We're working on it. But what I would definitely say is that as we take the training wheels off, we also have to worry about noise and errors in the quantum computer, because there's no error mitigation so far, and this is analog. We don't have fault tolerance or anything close to fault tolerance. So we need to think about that and come up with error mitigation strategies to see how well we can do. And at this point, I don't have a definite answer for that.